Since episode 1 of this series, we have been modeling stock prices with geometric Brownian motion, smooth, continuous, random paths that never jump. Every model we have built so far, from Black-Scholes to Heston, assumes the price path has no gaps. On October 19, 1987, the Dow Jones Industrial Average fell 22.6% in a single day. The S&P 500 dropped 20.47%. Now, under our Brownian motion model with 20% annual volatility, a daily move of that size is almost 18 standard deviations from the mean. The probability? Roughly 10 to the negative 71. That is a 1 followed by 71 zeros in the denominator. The universe is only about 10 to the 17 seconds old. Black-Scholes says this crash should never happen. It happened anyway. Let us run the experiment. Here are 100 stock price paths, all generated by geometric Brownian motion with the same volatility. The red dashed line marks a 20% single-day drop, the scale of Black Monday. How many of our 100 paths produced a crash that severe? 0. Not a single one. The model that powers almost every option on Wall Street cannot produce the most important event in modern market history. Here's what mathematicians did about it. In this episode, we will build the mathematical machinery that lets stock prices jump. From Poisson processes to Merton's Nobel-winning Jump-Diffusion model to the modern framework of Lévy processes, this is the math behind market crashes. Forget stocks for a minute. How do we count things that happen at random instants? Lightning strikes during a storm, earthquakes along a fault line, server crashes in a data center. These events arrive at unpredictable times, but on average, they happen at a steady rate. Watch. Events pop in along a timeline. Each red dot is one arrival, and above, the blue staircase counts them. Every step up means one more event. This staircase is what mathematicians call N of t, the counting process. The Poisson process makes this precise. If events arrive at an average rate of lambda per year, the probability of seeing exactly k events in time t follows this formula. Let us set lambda equal to 3, meaning on average 3 events per year. Here is the probability distribution for 1 year. The most likely outcomes are 2 or 3 events, each with about a 22% chance. 0 events? Only about 5%. 6 or more? Around 8%. And notice something elegant. The mean and the variance of n of t are both exactly lambda times t. For a Poisson process, the average tells you the spread. There is a beautiful structure hiding inside those random dots. The waiting time between consecutive events, tau sub y, follows an exponential distribution. This distribution is memoryless. No matter how long you have waited, the expected time to the next event is always 1 over lambda. Let us look at our timeline again, with the gaps between events highlighted. Each gap is an independent draw from the same exponential, and this gives us the crucial property, independent stationary increments. What happens in one time interval tells you absolutely nothing about what happens in any other non-overlapping interval. This independence is precisely what makes the Poisson process the natural model for random shocks. One last piece before we add size to these jumps. Take n of t and subtract its expected value, lambda times t. The result, m of t, is a compensated Poisson process. Watch. It drifts down between jumps, then jumps up by 1 at each event. On average, the downward drift exactly cancels the upward jumps. That makes m of t a martingale, a fair game with 0 expected future change. This compensated process is the mathematical skeleton that Robert Merton will build his Jump-Diffusion model on. A Poisson process tells you when, but a real market shock is not just a tick on a counter, it has a size. Black Monday was not +1, it was minus 22%. Here is the Poisson counting process from the last section. Every step is the same height, +1. Now watch what happens when we give each event its own random size. Some jumps are small, some are large, some go up, most go down. This is a compound Poisson process. Formally, the compound Poisson process J of t is the sum of random variables y sub I, one for each Poisson arrival, all independent and identically distributed. Crucially, the jump sizes are independent of the timing. When a jump happens does not affect how big it is. Robert Merton made a specific choice. He said the logarithm of each jump size y follows a normal distribution with mean mu j and variance sigma j squared. Here are 500 simulated jump sizes. Notice how most jumps cluster near the mean mu j equals -0.05. That negative mean reflects the empirical fact that in equity markets, crashes are more common than booms. The normal curve fits beautifully. There's a clean formula for the moments of J of t known as Wald's identity. The expected value of J is simply lambda t times the expected value of a single jump. The variance is lambda t times the second moment of a single jump. More frequent jumps and bigger jumps both increase the total variance. And just like the plane Poisson, we can compensate, subtract the expected drift, and what remains is a martingale. Mathematicians encode this structure in a single object called the Lévy measure, nu of dx equals lambda times the jump size density. We will return to this in the final section. Now we have all the ingredients. Brownian motion for the smooth, continuous part of a stock's daily wandering. Compound Poisson for the sudden, discrete shocks, the crashes, and the spikes. Robert Merton's insight was to glue them together with a plus sign. That plus sign won him a Nobel Prize. In 1976, Robert Merton wrote down an equation that changed finance. Take the percentage change in stock price, set it equal to three pieces. First, a drift term, mu minus lambda k bar times dt. Second, the Brownian motion we know from episode 1, sigma times dw. This is the smooth, continuous randomness. Third, the new ingredient, y minus 1 times dn, a random jump of random size arriving at Poisson times, geometric Brownian motion, plus random shocks. That is the entire idea. Now let us see what this equation does. On the left, geometric Brownian motion, the smooth model from episode 1. On the right, Merton's Jump-Diffusion. Here is the key. Both paths use the exact same Brownian noise. Identical random numbers. Watch the GBM path draw itself. Smooth, continuous, no surprises. Now watch the Jump-Diffusion. Same underlying drift, same Brownian wiggle, but sudden vertical gaps appear, red lines marking the moments where the Poisson process fires. Same noise plus jumps equals a completely different world. You may have noticed a strange term in the drift, minus lambda k bar. K bar is the expected relative jump, e to the mu j plus sigma j squared over 2 minus 1. With our parameters, that is about negative 4.4%. Why subtract it from the drift? Because each jump changes the stock price on average by k bar. Without the compensator, the drift would be mu plus the expected jump effect. The minus lambda k bar cancels out the jump contribution, keeping the overall drift exactly equal to mu. And here is the trap. The most common mistake in jump diffusion is forgetting the sigma j squared over 2 inside the exponential. That is the Jensen's inequality correction, the same kind of correction that gives us the Ito term in geometric Brownian motion. The closed-form solution is surprisingly elegant. The stock price equals S0 times an exponential, the familiar GBM piece with its Ito correction, multiplied by the product of all jump factors y sub I up to time t. And notice, if we set lambda equal to 0, the Poisson process never fires, the product is empty, and we recover exactly the GBM solution from episode 1. Merton's model is a strict generalization. Everything we built before is a special case. Now comes the real question. How do we price options in a world where the stock can jump? Here's the most beautiful result in jump diffusion theory. Suppose we somehow knew that exactly n jumps occurred during the life of the option. Then the log of the stock price at maturity is the sum of a normal Brownian piece plus n independent normal jump sizes. A sum of normals is normal. So conditionally on n jumps, the log price is Gaussian, and we are back in a Black-Scholes world, just with an adjusted volatility sigma n and an adjusted interest rate Rn. The option price is then just a weighted average. For each possible number of jumps, compute the Black-Scholes price with adjusted parameters, then weight by the Poisson probability of that many jumps. Here it is, Merton's option pricing formula. The call price equals an infinite sum. Each term is a Poisson weight. The probability of exactly n jumps under the adjusted intensity lambda prime, times a Black-Scholes price with adjusted parameters. Sigma n squared equals sigma squared plus n sigma j squared over t. More jumps means higher effective volatility. Rn adjusts the risk-free rate to absorb the drift from those n jumps. Two traps to watch for. Sigma n has a divide by t that is easy to forget, and Rn uses the original lambda, not lambda prime. Let us watch the formula work. Each bar represents the contribution of one term in the Merton series. Term 0, no jumps at all. This is a pure Black-Scholes price with elevated rate, contributing $2.30. Term 1, Exactly one jump. The largest single contribution, $3.86. Term 2 adds 325. Term 3, 184. And the remaining terms taper off quickly. By the seventh term, the series has essentially converged. The total, $12.40. That is the Merton Jump-Diffusion price for an at-the-money call on a stock with 2 expected jumps per year. Now let us put this in context. The Black-Scholes price for an at-the-money call with our parameters is $10.45. The Merton price, $12.40. That difference, $1.95, is the jump premium. It is the extra cost of insuring against a world where the stock can crash without warning. Every time you buy an option, part of the price you pay reflects the market's belief that jumps are real. Next, we will see how this jump premium reshapes the implied volatility smile. Black-Scholes implied volatility should be a flat horizontal line, 1 sigma for every strike price. That is what the model predicts. But we saw in episode 15 that the market paints something very different. The question is, which model draws which shape? Let us build a gallery. First, Heston's stochastic volatility from episode 15. When spot and volatility are negatively correlated, the left tail gets fatter. OTM puts become expensive, OTM calls become cheap. The result is a downward sloping skew. Now Merton's jump-diffusion with symmetric jumps. When the mean jump is 0, crashes and spikes are equally likely. Both tails get fatter. The result is a U-shaped smile, symmetric around the at-the-money strike. Finally, Bates. Take Heston's skew, add Merton's jumps. The combined curve has a steep left side. The skew from stochastic volatility, plus a gentle uptick on the right, the smile from jumps. This is the shape real markets draw. There is a forensic test that tells you whether jumps are present. Look at very short maturity options. Under pure stochastic volatility like Heston, the smile flattens as the maturity shrinks towards 0. The continuous diffusion does not have time to create fat tails, but under Merton, the smile persists. Even at short maturities, there is a finite probability of at least 1 jump, roughly lambda times t. That probability is linear in t, which means out-of-the-money option prices are also of order t, not exponentially small. A non-vanishing short maturity smile is the smoking gun for jumps in the data. The Bates model from 1996 combines both. It takes Heston's stochastic volatility engine and adds Merton-style jumps on top. In episode 19, we will calibrate these models to real option data and see which combination the market actually believes in. But first, these same jump equations have a secret life outside of finance. The Poisson process we built today is not just for stock markets. Add one twist, make the arrival rate depend on past events, and you get a Hawks process. Each event excites the rate, triggering cascades. Twitter retweet storms, earthquake aftershocks, and high-frequency order flow all follow this math. The same Poisson likelihood we used for pricing, the product of rates at event times the survival probability. This exact formula trains neural networks to predict when the next hospital visit will happen, or when a user will send their next message. In reinforcement learning, an agent can face sudden catastrophic state changes, a robot falling off a table, a game character dying. These are compound Poisson shocks in the transition model. And in Bayesian deep learning, the spike and slab prior is a mixture of a point mass at 0 and a Gaussian. That is literally a jump-diffusion prior over the space of neural network weights. The jump is universal. Every model we have seen in this episode, and in fact every model in this entire series, is a special case of one mathematical object, geometric Brownian motion from episode 1. Merton's jump-diffusion, Kuh's double exponential, Bates's stochastic volatility with jumps. They all live inside a single framework called the Lévy process, characterized by just 3 ingredients, a drift gamma, a Brownian component sigma squared, and a jump measure nu. The Lévy-Khintchine formula is the master equation. It says the characteristic exponent of any Lévy process has exactly 3 pieces. The characteristic function is just e to the t times psi. Now here's the zoo. Merton's model has a Gaussian jump measure, finite activity, meaning a countable number of jumps per year. Kuh replaces the Gaussian with a double exponential, still finite activity but with fatter asymmetric tails. The variance gamma model goes further. Its jump measure diverges at the origin. Infinitely many tiny jumps every instant, no Brownian motion at all. Finite versus infinite activity is the fundamental dividing line in the Lévy world. The Lévy-Ito decomposition tells us exactly what any Lévy process is made of. 4 pieces and only 4. A linear drift, a continuous Brownian motion, compensated small jumps, the infinitely many tiny ones near zero, and uncompensated large jumps, the rare big shocks. Set the jump measure to 0, and the last 2 pieces vanish. You are left with drift plus Brownian motion. That is GBM. That is episode 1. Every model we have built is a chapter in the Lévy story. So here's the deepest lesson of this episode. The right mathematical object for finance is not Brownian motion, but the Lévy process. Brownian motion is just the special case where the jump measure is 0. Once you see that, every model in this series, past and future, finds its place inside a single landscape. In the episodes ahead, we will build on this foundation, yield curves, credit risk, and ultimately calibrating all of these models to real market data. Thank you for watching, and I will see you in the next one.